Dead reckoning is the method of determining a ship's position by applying to the latest well-determined position the run that has been made since that position was established. For this purpose, only the true courses steered by the ship are used. By multiplying the speed by the time on the course, the distance along the course is determined. In keeping dead reckoning, no allowance is made for current. An old method of keeping account of a ship's position, which required use of a complicated table in Bowditch and an involved computation or deduced reckoning, was the origin of the term dead reckoning. Dead reckoning in modern practice is almost universally kept by a graphical solution on a chart of the locality or upon plotting sheets printed by the hydrographic office. The navigator keeps a notebook from which he makes up a table of times, courses steered, and speeds of the ship, such as this. Having these data available, he can plot his courses and distances and predict his dead reckoning positions. This is known as DR plotting. For illustration, let us suppose that at 0500, the navigator of the USS Savannah has fixed his position here. Note that the position is marked 0500 fixed, and that it has a small circle around it. From the table of courses and distances he has prepared, we see that at 0500, the Savannah was steering 0602 until 0554, at which time she changed course to 078. Before he commences plotting, the navigator checks his drafting machine to ensure that it is lined up with the compass rose. You can see that it is a little in error, as being set on 090, it does not line up with the 090-270 line of the compass rose. So he casts loose the clamps, lines it up thus, and sets up the clamps again. A careful navigator always checks at frequent intervals the alignment of his drafting machine with the compass rose. Now he sets his drafting machine to 060 degrees and moves it until the edge of the ruler is at the 0500 fix. From the fix, he draws a line in the direction of the course. Note how he labels this course line. Course 060, speed 15. From the table of courses and distances, we see that the Savannah remained on this course until 0554, or 54 minutes. This was a distance of 13½ miles. Watch how the navigator measures the distance, always on the latitude scale, which we remember is in miles, never the longitude scale, which is in minutes of longitude. Note that he sets his dividers so that he measures the distance 13.5 miles exactly opposite the course run. He does this because the latitude scale on a chart varies and is correct for plotting only at the mid-latitude of the course line. Plotting this distance along the course line, he puts a half circle around the dot and labels this position 0554 DR. Now he plots the next course, 078, and labels it. The ship is on this course 46 minutes, or 11.5 miles. He plots this position and labels it 0640 DR. Continuing, he lays down his DR position to 1200, or zone noon. So we see how a navigator plots his DR position from a well-determined position along the course line for a distance equal to speed multiplied by the time run on the course. If DR plotting were entirely accurate, we would not need any other kind of navigation. Unfortunately, 4 factors contribute to error in DR positions. First, the course may be wrong because no steersman can keep an ordered course exactly, or the gyro compass may have an unknown error, or the deviation of a magnetic compass may not be exactly known. Second, the speed may be in error because the engines are not making their ordered speed due to inattention at the throttles or because of a foul bottom. Third, the flow of water in which the ship travels, called the current, sets the ship off its course and speed. Fourth, the wind has an effect on a ship, tending to blow it off its course or to slow or increase its speed through the water. It is for this reason that from time to time we must fix our position on the surface of the seas. To do this, we make celestial observations of the sun, moon, stars, and planets, our lighthouses in the sky. You will remember that if the navigator observes the altitude of a star at a certain time, he will obtain the same altitude as will another observer who is on the opposite side of the geographical position or subastral point of the star and is at the same distance from it. If we view this diagram from above the star, it is evident that any observer at the same distance from the geographical position would observe the same altitude at the same instant. If the navigator observes 2 stars, he establishes 2 circles, one about each star's geographical position, at one intersection of which is the location of the ship. This is the principle of circles of equal altitude. If we enlarge the scale of the chart to one on which we can plot, the geographical positions of the stars are ordinarily beyond the limits of the chart. Also, the segments of the arcs of these circles on a chart of this scale are very nearly straight lines. For the purpose of navigation, short segments of the arcs are considered to be straight lines and are called lines of position. The bearing of the body from the DR position of the ship is established by the azimuth. This angle is measured from the north direction of the meridian, clockwise, to the bearing line of the geographical position. If we know how far the actual line of position is from our DR position, and whether it is toward the body or away from it, we can draw in the line of position on which we are located. We know that it is always perpendicular to the bearing line of the geographical position. You will remember that we can compute this distance A from the DR position to the actual line of position, and also the bearing of the geographical position, Zn, by solution of the astronomical triangle. Thus we can determine quite accurately the position of our ship any time that we can get good observations of 3 or more lighthouses in the sky. Let us follow the Savannah as she steams west until evening twilight. At 18:20, with the help of his assistant navigator and another officer, the navigator obtains simultaneous observations of 2 stars and a planet. After working out the sights, he has these data. Let us watch him plot these lines of position. First, he plots the latitude computed from a sight of Polaris. He sets his drafting machine parallel to this latitude line, measures up this meridian 13 minutes, and draws in the latitude line. Note how he labels it: 1820 for the time of the sight, and Polaris to keep track of which body is observed. Next, he plots the line of position from Sirius. Just as in laying down a course, he sets his drafting machine on the azimuth 151 true. This time he checks it by moving the ruler to the compass rose. The ruler checks on 151 and the reciprocal 331. And so he knows that the drafting machine is properly aligned with the chart. From the 1820 DR in the direction 151, he puts a star, but he also draws the line in the other direction, because the line of position from Sirius is away from the DR position 1.2 miles. Observe that he measures this distance on the latitude scale and directly opposite the DR position. Note the use of a triangle for plotting the line of position perpendicular to the azimuth line. Now he is ready to plot the planet Mars, ZN 083, altitude difference 5 miles, toward the body this time. See how he circled the position and labeled it 1820 fixed. However, the navigator usually takes all the sights himself, and this necessitates his running lines of position forward to compensate for the time interval between sights. Let us see how this is done. At 0910 the next morning, the Savannah's DR position is as shown. The navigator observed the sun, and now he plots it, ZN 087, 5 miles toward. It can be seen that while this gives him a very accurate longitude, all he knows for sure is that he is somewhere on this line of position. If he had been able to obtain another line of position to cross with this line, he could fix the position of the ship. Other bodies are not always available in the daytime, but he knows that at local apparent noon, the sun will be on the meridian, and he can get a very accurate observation for latitude. Between 0910 and noon, however, maneuvers are held. Let us see what effect they have on this 0910 line of position. We see the ship with the line of position connected to its bridge by ZN and A, the azimuth and the altitude difference. No matter how the ship changes course and speed, the line follows along, bearing 087, distant 5 miles, until it reaches the local apparent noon DR position. Thus we see all the navigator had to do to bring it forward was plot his DR position up to LAN, and from that DR, plot ZN 087 and altitude difference 5 miles toward. Note that the line is now labeled 0910 1154 sun, which means that it is a 910 sun line advanced to 1154. Plotting the latitude line that he has obtained from a meridian altitude of the sun at noon, he labels the position where the two lines intersect 1154 running fix. The reason this is called a running fix is that the 0910 1154 line is subject to all the errors of DR plotting which we have previously noted. That is, errors in course, in speed, or due to wind or current. If the DR plot is in error because of any of these causes, then so is the line of position which travels along with it. For this reason, we do not run lines of position forward for more than 5 hours. To determine whether or not a running fix may be considered a relatively good position requires a nice judgment on the part of the navigator. The navigator of the Savannah considers that he has a good steersman, reliable engineers, and that there has been little or no wind or current. And so he decides to call his running fix a well-determined position and run his DR plot forward from the LAN running fix.